Have you ever really thought about the difference between the flash of a firework and the slow crawl of rust on an old nail? I mean, they're both chemical reactions, right? They're both changing one thing into another. So today, we're going to unravel two of chemistry's biggest secrets: why these reactions happen in the first place, and what in the world decides how fast they go.
It's such a huge contrast when you think about it. On one hand, you've got an explosion, this brilliant, powerful blast of energy that's over in a blink. And on the other, you have rust forming on iron, a process so slow you might not even notice it from one day to the next. One's an all-out sprint, the other is a marathon that can literally take years.
So what gives? The difference here isn't some kind of magic, it's just chemistry. And it all boils down to two really fundamental questions. Number one, is the reaction even likely to happen? And number two, if it is, what's stopping it from happening instantly? If we can answer those, we can understand pretty much everything, from how our bodies get energy from food to how we power our cars.
Okay, let's tackle that first big question: energy. I want you to picture a big boulder sitting on top of a hill. See, nature loves to move from a higher energy state to a lower one. It's just easier. So for our chemical reaction, the big question is, does it naturally want to roll downhill? When it does, we call that an exothermic reaction. It's just like our boulder rolling down the hill. As it tumbles, it releases all that potential energy. In chemistry, that energy is usually released as heat. A campfire is the perfect example, right? The wood starts out packed with stored chemical energy. As it burns, it releases that energy as heat and light. And what's left behind, the ash, has way less energy. Now, the opposite of that is an endothermic reaction. This would be like trying to push that same boulder up the hill. It's not going to happen by itself. You've got to put energy into it. Those instant cold packs you use for injuries, that's what's happening there. You break the little pouch inside, and a reaction kicks off that has to absorb heat from its surroundings, which is why the pack feels so cold. It's literally pulling energy in to make the reaction go. And this whole idea is built on one of the most fundamental laws of the universe. Energy isn't just created out of thin air or lost forever. When a reaction gives off heat, that energy was already hiding in the chemical bonds of the starting materials. And when a reaction gets cold, that energy is being packed away into the bonds of the new stuff being made. It's just moving around. So here's the key takeaway, a really simple but powerful idea. You always have to put some energy in to break bonds apart. But you get an energy payoff when new, more stable bonds snap together. Whether a reaction is exothermic or endothermic just depends on which one of those is bigger, the energy you put in or the energy you get out. Okay, so if these energy-releasing reactions are like a boulder just waiting to roll downhill, that brings up a really important question. Why aren't they all happening like right now? Why doesn't a log just burst into flames all by itself? This brings us to the second fascinating part of our puzzle: reaction speed. Seriously, think about it for a second. Paper, wood, gasoline, all of these things are absolutely packed with stored energy, just waiting for a chance to be released in a nice, downhill, exothermic reaction. So what's stopping the whole world from being in a constant state of fire? There must be some kind of barrier, right? Some kind of speed bump that has to be cleared first. And that barrier has a name. It's called activation energy. It is that little push you have to give the boulder to get it over a small hump at the very top of the hill before it can go crashing down. For a fire, that activation energy is the spark from a match. It's that initial jolt of energy you need to start breaking the very first chemical bonds. So this little chart basically maps out the whole energy journey. You start with your reactants. They're at a high energy state. Then you have to add a little energy, the activation energy, to get them over that speed bump. That peak is the highest energy point, called the transition state. And once you're over that hump, it's all downhill to the products, which are sitting in a nice, low-energy, stable state. So we've got this great analogy of an energy hill and a speed bump. But what does that actually look like for the tiny little molecules involved in the reaction? Well, let's zoom way in and see what's really happening down at the microscopic level. This gets us to the core of what's called collision theory. Now, for molecules to react, they have to physically bump into each other. But, and this is the whole secret, most of the time when they collide, nothing happens. They just bounce off each other like tiny billiard balls. Only a very small fraction of all the collisions are what we call effective. So what makes a collision effective? It really comes down to three rules:
Rule 1, they have to actually collide. Pretty obvious. Rule 2, they have to smack into each other hard enough with enough energy to get over that activation energy barrier we keep talking about. And rule 3, which is super important, they have to hit each other in exactly the right way with the correct orientation, kind of like two puzzle pieces clicking together perfectly. Yeah, this slide shows it perfectly. Over on the left, you've got an ineffective collision. Maybe they didn't have enough oomph, or maybe they hit at a weird angle. The result? Nothing. They just ricochet off, totally unchanged. But on the right, boom, a successful, effective collision. They hit with enough energy at just the right angle, and that allows the old bonds to break and new ones to form. That's a chemical reaction.
And you know, this is where things get really, really cool. Because if we understand the rules of the game, the rules for an effective collision, we can start to bend them to our will. We can become masters of chemical speed, hacking the reaction rate to make things go faster or even slower whenever we need to.
And we have 4 main tools in our toolbox to do this. We can crank up the temperature, increase the concentration, increase the surface area, or we can add a special little helper called a catalyst. Now, temperature, concentration, surface area, they all basically lead to more collisions. But that last one, the catalyst, well, that's a whole different kind of trick. Let's break these down. First up, temperature. When you heat something up, you're just giving its molecules more energy, making them zip around like crazy. And this helps in 2 ways. 1, since they're moving faster, they're going to collide more often. And 2, when they do collide, more of them will have enough energy to actually clear that activation energy barrier. So it's a double whammy for speeding things up. Next, concentration. This one's pretty easy to picture. If you pack more molecules into the same amount of space, you're basically turning a big empty hall into a crowded party. The particles are just going to bump into each other way more often, and that increases the odds that one of those bumps will be an effective one. All right, now for our secret weapon, the catalyst. So what is it? Simply put, a catalyst is a chemical shortcut. It's a substance you can add to a reaction that makes it go way faster. But, and this part is just amazing, it doesn't get used up in the reaction itself. It's like a chemical matchmaker that helps everyone get together and then just walks away unchanged. So how on earth does it work? Well, a catalyst offers the reaction a completely new route to take, an alternate pathway that happens to have a much lower activation energy. It basically just lowers that speed bump we've been talking about. And with a smaller hill to climb, way more molecules have enough energy to make it over, letting the reaction take off. And the effect isn't small. We're talking about a dramatically faster reaction rate. Catalysts are absolutely essential. They're at work in our bodies as enzymes, helping us digest food, and they're in our cars as catalytic converters, cleaning up harmful exhaust fumes. They're everywhere.
So let's bring this all home. We started with 2 big questions. The first one was, why does a reaction happen at all? The answer is all about thermodynamics. Is the reaction releasing or absorbing energy overall? Is it rolling downhill? And the second question, how fast does it happen? Well, that's the world of kinetics, and it's all about that activation energy barrier and the rules for a successful collision.
And that leaves us with a really powerful thought. Now that we know the rules of the game, what could we do with them? What everyday reactions could we speed up or slow down to really change things? Could we speed up the process of creating cleaner fuels? Or slow down the rusting of our bridges and buildings? See, understanding how chemical reactions work doesn't just explain the world around us, it gives us the tools to actually start changing it.